Section 6.4, to state the properties of special parallelograms. The properties of the parallelograms apply to a rhombus, a rectangle, and a square. We're going to look at more properties that apply to them, but always recall that these properties of a parallelogram apply to all of these figures. And that is that both pair of opposite sides are parallel, both pair of opposite sides are congruent, both pair of opposite angles are congruent, and the diagonals bisect each other. Our first property, Theorem 6.9. Each diagonal of a rhombus bisects two angles of the rhombus. Here I'm given LMQP is a rhombus. Remember, all properties of a parallelogram apply. This extends a little bit further to a rhombus that each diagonal bisects two angles. So diagonal LQ bisects this angle into two congruent angles. It also bisects this angle into two congruent angles. And if you notice, I used single arcs for all of them. That's because each of these angles are congruent. The entire angle, MLP, is congruent to the entire angle, MQP. For example, if I stated that that would be 100 degrees, then this angle would be 100 degrees. And if they're being bisected, that means it would divide this angle to two congruent angles, 50 degrees and 50 degrees. Therefore, this would be 50 degrees and 50 degrees. Multitudes of ways to get that. By this theorem, or alternate interior angles, are just two of the ways that we could use to get those angles congruent. With this information, that this is 100 degrees, I know that this angle, LMQ, has to be 80 degrees. That is because they are same-side interior angles and supplemental. Also, remember that each diagonal cuts the angle into two congruent angles. Therefore, this would be 40 degrees and 40 degrees. And these two angles would be both 40 degrees. This theorem can help us identify angles in a rhombus. Therefore, if I would know one angle in the rhombus, I would be able to determine all angles in the rhombus. Theorem 6.10 states the diagonals of a rhombus are perpendicular. Here we have a rhombus, U, V, W, X. And recall from the previous slide that each diagonal bisects two angles of the rhombus. So if I would just let angle VUX equal 120 degrees, I would then know that this angle is being divided into two congruent angles, each being 60 degrees. And if that's true, I know since VUX, the angle is 120, the angle UVW must be supplementary to it because they're same-side interior angles. Therefore, this angle must be 60 degrees. And since this diagonal divides these two angles into two congruent angles, each of those would be 30 degrees. And of course, I could make these angles both 60 and these angles both 30. And if I take a look at each triangle inside the rhombus, I can use the triangle sum theorem, and notice I have two acute angles that add together. They give me 90. Therefore, this would be 90 degrees. And then that would tell me that diagonal UW is perpendicular to VX because these two lines intersect to form right angles. And that verifies Theorem 6.10. If I go back a slide, we can see the same thing occurred. I have my four triangles in my rhombus, and the acute angles add up to 90 degrees. Therefore, the third angle in the triangle, by the triangle sum theorem, would also have to be 90 degrees. Again, I have line LQ perpendicular to MP because two intersecting lines form right angles. Our next theorem is 6.11, and this states the diagonals of a rectangle are congruent. Remember that all properties of a parallelogram apply to a rhombus, a rectangle, and a square. Therefore, in this rectangle, I know that RC, the diagonal, bisects ET, and ET bisects RC. So RA is congruent to AC, RE is congruent to AT. But theorem 611 takes this step a little further. This tells me that segment RC is congruent to segment ET, which means the diagonals are congruent. But since these diagonals are bisected, that tells me that all of the segments interior to the rectangle are congruent. Therefore, RA is congruent to EA, which is congruent to TA and CA. And when we look at that information, I am now given 4 isosceles triangles inside my rectangle. Therefore, I can start creating congruent angles inside that because I know the isosceles triangle. If 2 sides of a triangle are congruent, then the angles opposite those sides are congruent. And that would make it very easy for me to get this triangle, RAE, congruent to triangle TAC. Similarly for triangle RAT and EAC. But I can use the isosceles triangle theorem on all triangles inside this rectangle. And that would help me identify angle measures. For example, I do know a property of a rectangle is that they have 4 right angles. If I know one angle, for example, if this was 30 degrees, I could then determine all the angles. Since this is a right angle, this would be 60. By alternate interior angles, this would be 60. I know that these 2 angles are congruent, so that would be 60. Complementary angles, this would be 30. By the isosceles triangle theorem, this is 60. This would be 30. And by the isosceles triangle theorem, this is 30. Then I could use the triangle sum theorem to determine the interior angle measures surrounding point A. 30 and 30 is 60. This would be 120. Supplementary angles would give me 60. A square. A square has all the properties of a rhombus and a rectangle, and also the properties of a parallelogram. Therefore, each diagonal bisects 2 angles. The diagonals are perpendicular, and the diagonals are congruent. Here I have square ABCD. I know that all sides are congruent. I know that the diagonals are congruent. Therefore, AC is congruent to BD. And since they bisect, that tells me that AM is congruent to BM, congruent to CM, and congruent to DM. Therefore, as you can see, I have 4 isosceles triangles. As a matter of fact, they are 4 right isosceles triangles because I know that the diagonals are perpendicular. Also, since this is a square, it has properties of a rectangle. Therefore, there are 4 right angles. And since the diagonals bisect each angle, that tells me that this is a 45-degree angle, 45, 45, 45, and so on. Now you can tell that I have 4 isosceles right angles in my square. On this slide, we're given a square, EFGH, and they want us to find the measures of all the angles. As stated previously, we know that the diagonals are perpendicular. Therefore, here are 4 right angles. The square itself has 4 right angles because it has properties of a rectangle. And each of the diagonals bisect 2 angles. Therefore, this is 45 degrees. As a matter of fact, all the acute angles are 45 degrees. And of course, this was stated on the previous slide. But I think I just wanted to demonstrate how easy it was to find angle measures in a square. They're always going to be in this fashion. Here we're given a rectangle again, ABCD, and we want to find the following. We want to find the length of DC. DC is the right side of my rectangle. It is congruent to the left side, AB. Therefore, this is 6 inches. EC. EC is part of this diagonal. In a rectangle, I know that diagonals bisect. Therefore, EC is 5 inches. They want to find the length of BD. BD is congruent to AC. We already found that EC is 5 inches. Therefore, AC is 10, which must be congruent to BD. Therefore, BD is 10 inches. Now what we want to do is find the length of BC. Here, it's a little bit more difficult, but we have to take a look at part of this rectangle. I know that in a rectangle that the vertices have a measure of 90 degrees. There's 4 right angles. And what I want to do is take a look at just this right angle. For that matter, this right triangle, ABC. And for that right triangle, I have a length of a leg that's 6 inches, and the hypotenuse, which is 10 inches. And notice I used those definitions for a purpose. I have a leg and a hypotenuse. I also have another leg. And to determine this length, all I need to do is use the Pythagorean theorem. And remember, the Pythagorean theorem is the sum of the legs, a squared plus b squared. Sum of the legs squared equals the hypotenuse squared. Now I just substitute in. I can let a and b be either leg, but they are legs. So I'm going to let this be 6 squared, which is 36, plus b squared equals c squared, which is 100. Here we're given rectangle ABCD. We want to find the measure of all the numbered angles in our rectangle. Here we have a 23-degree angle. I know in a rectangle that all the angles are right angles at each vertice. Therefore, I can find complementary angles. Since this is 23, 90 minus 23 is going to give me a 67-degree angle. I also know, since this is a rectangle, that AC is congruent to BD and that these diagonals bisect. Therefore, I know that these segments are all congruent, creating isosceles triangles. Since this is 23 degrees, angle 4 is 23 degrees by the isotriangle theorem. If two sides of a triangle are congruent, the angles opposite are congruent. And it follows that angle 6 is 67 degrees for the same reason. I can determine that angle 5 is 67 degrees because if two parallel lines are cut by a transversal, then alternate interior angles are congruent. 7 can be determined because of complementary angles. Therefore, this is 23 degrees. Now all I need to do is determine angle 1, 2, and 3. I can use the triangle sum theorem to do this. Here I have 67 plus 67, which is 134 degrees. 134 from 180 is going to give me 46 degrees. And I know I can find angle 3 because they're supplementary, and that's going to give me 134 degrees. And these are vertical angles, which is also 134 degrees. I can also use our exterior angle theorem for 2 and 3. The exterior angle is equal to the sum of the remote interiors. 67 plus 67 is 134. So we could have gotten that angle and angle 2 in that fashion. Of course, we can determine the other angles in similar fashion to fill out all the angles of this rectangle. Subtract 36 on both sides. I'm going to get b squared equal to 64. I take the square root of both sides, and I get b equal to 8. Therefore, the length of BC is 8. Here I want to determine the measures of all the angles in this rhombus. Recall a rhombus has 4 congruent sides, and the diagonals are perpendicular, and each diagonal bisects 2 angles. Here I'm given a 38-degree angle. I know that this diagonal bisects this angle and this angle. Therefore, if this is 38 degrees, this must also equal 38 degrees. Since I bisected this angle, the whole angle has to be 76 degrees. I can determine that these two angles are congruent to these two, either by alternate interior angles or just knowing that the entire angle has to be congruent to this entire angle. Therefore, when they're bisected, they also are congruent. Therefore, both are 38 degrees. I also know that these diagonals are perpendicular. Therefore, I'm given a right triangle. By the triangle sum theorem, I know that 90 and 38 is going to give me 128 degrees. And 128 degrees from 180 is going to give me 52. Again, this diagonal bisects these two angles. Therefore, this must be also 52 degrees. And if that's true, this whole angle is 104. As I said over here, this whole angle is 76. And that should be the case because the entire angles here and here are same side interiors. Therefore, they have to be supplemental. And 104 and 76 is 180. Now, since this is 104, this also is 104. And therefore, it's bisected by this diagonal, which is 52 and 52. Or I also could say alternate interior angles. And again, all of these angles are right angles. And notice what I end up with is 4 congruent right triangles.